So we'll just start that. Yeah. So yeah. So which problem from line?
Uh,
Hmm.
Nine. No, I just need a clarification. It says a box cuboid shape is made out of the cardboard. This means it's
Hmm.
not an open box; it's a closed box.
Yeah, it's a closed box. Where is that? Let me check this.
Question number 10.
Okay, graded assignment cell question number 10. So it's a closed one.
Okay,
Uh,
that's the
yeah,
yeah
but
because
it doesn't matter, I guess.
no, it
Is
batters the top. It batters because that the because the tutorial had a exercise problem which
okay, okay, yeah, it
specifically
will
talks
matter.
about
It will matter. Yeah,
yeah.
because it's asking about the area. Okay, okay, yeah, it will matter.
Other than that, I have quite a few conceptual questions in this
Okay,
week.
so we'll start from the first. Okay,
Yeah, yeah.
the constant optimization. So I'll just open the slide. Mm. So yeah, so in the first like lecture, it's like just the basic like stuff. Like here in the last week, we were solving the optimization problem with without any conditions. So here we are doing with some condition that is a constant. Like it's a type of condition that we are applying. So gx less than equals to 0 is a condition that we are applying to get the minimum x while solving the optimization problem, that is fx. Okay. So last week we were not like there was a problem and that we were solving. So that can be solved with some gradient descent or some other stuff. So here we are solving, but there are like some conditions also given. Okay. So here the professor is discussing, right? Let us have a value x star that is satisfying our condition. So let's, like for example, I'm solving a problem that is we need to get the minimum of x of a function fx such that the condition is that the x whatever we are taking should satisfy this condition also, that the gx should be less than equals to 0. For that, let's let us assume that we are claiming x star is the solution for this problem, that optimization problem that we are solving. Okay. If x star is the optimum, then it should satisfy both the conditions, right? So at x star, the function's value should be minimum, and it should also satisfy the condition also that has been given. That should satisfy. Like the g x star should also be less than equals to 0. For that, the first thing that anybody will check is whether this is satisfying our constant or not. Like for example, if it's a constant like x square plus y square is equal to, like the point should lie on a circle. So that point must lie on that circle. Okay, so that is our constant. That is the condition that we need to apply. Okay, so this is the first step that we are checking. Okay, if star is like satisfying our condition, then it's fine. So the second condition is if we are checking x star is the only solution or the optimum solution, then there should not be any descent direction. Descent direction, simple word, I can tell you, like descent direction is that direction in which the value of the function decreases. So if I'm getting x star as the optimum solution, then there must, like if I'm just plotting a quadratic equation that is going downward, okay, like no going upward. Okay, it's a ball, simple ball. So at the bottom of the ball, let's for example that is the x star. Okay, so you can't say like from there is any direction where the value of x star or the function's value will decrease. Like I'll just plot that. So for this, let's for example I have this as a plot. Okay, so this x star. So from here we don't have any direction where the function's value will decrease, right? So yeah, but if I'm taking this as x star, so at least I have a decent direction. This direction is the decent where the function's value will start decreasing, right? So from here, if I'm taking this as x star, then yeah, we have a direction where the value of the function will decrease. But if I'm taking this as x star, then there is no like descent direction, right? So this is generally the descent direction. And the next point is, so no descent direction should be a feasible direction. So descent direction generally is applicable for the function. Function means like the any do I have any direction where the function's value is decreasing? If the answer is no, that is fine. Then x star is like, yeah, so this is satisfying one condition. And there's that descent direction should not be the feasible direction. Feasible direction is what? Feasible direction is those direction in which the functions that the gx should also satisfy. Okay. So like for example, I'm having some x star. And if that is satisfying our this condition that the x star when I'm putting in the function g, that is satisfying our condition that is less than equals to zero for this problem. So there must be some direction where we'll go, and in that direction the function's value will satisfy itself. Like the that must be a feasible direction. Feasible direction, like it's a simple, like you can think of like descent as the direction in which the function's value will decrease, and the feasible as the direction in which in which the whatever the value of the x star will take, that will satisfy the gx. That's it. So this is our the descent and the feasible direction. There should not be any confusion between those two. Okay, so there should not be any descent direction that is feasible also. Okay, if you are able to find even one, then this x star is not the optimum solution. You need to check for the other x star. Okay, so that is clear, right? Is that fine?
Sir.
Yeah.
If
So
if it so
Yeah.
happens that there is no descent direction,
Huh.
but there is a feasible direction, then what happens?
So there is a okay. So that will, so if you are already have the descent direction means you are able to find some point where the value is lesser than that, right?
No, I'm saying there is no descent direction.
Yeah,
Okay.
there is no, okay, there is no descent direction means this is the curve, and you are able
Yeah.
to get, right? So this is
Yeah.
the minimum.
But
Okay.
let's say for some function we've got there is no descent direction, but there is a feasible direction further. That
Okay,
does it
feasible,
happen at all?
yeah, it can happen, right?
Then what do
See,
we complete? What do we conclude? Then that's also not an optimal point.
that is, see, there will be so many points where the point where the point will be feasible. Feasible means that will satisfy the what you can say the gx, this condition. There will be n number of points, right?
Okay, okay, got it.
Right. So yeah. Okay. So yeah. So this is our this was our problem, and that we have sought out. So for this mathematically, how generally we go? Okay. So this was the like you can say this is a like statement that you need to understand. In mathematically, how will we show that? Okay, what is the descent direction? Was the feasible direction or not? Okay. So let's, for example, this is a basic Taylor series like fx plus eta d that generally we use in the gradient descent also. So this is the condition, and if you want this function to be lesser than this value, like fx plus eta d. So if you want to be this function should be lesser than that, then this should be negative, right? So like d transpose delta of fx should be less than equals to, and d is the descent direction, right? So there is no like confusion in this. So if I'm having the direction, so like for example fx star, like he just took some value x star, and if our the direction of the direction of the gradient of x star is this direction, this the arrow where it is been represented. So where you'll be finding where is the direction, where is the values, or where is the direction in which the dot product of this gradient of fx star and the direction should be less than zero. So that must be like if you are having the dot product as less than zero, then it must be the angle like it should lie here, right? So this is our feasible, sorry, the descent direction, right? And if you have the gradient of g, so you can expect like this is a g, some function g, and the gradient of this function is here. So the perpendicular or the dot product for this also, the same thing will apply for. So so like concentrate in this point. So if you are having this gx star, the gradient of gx star For this also, what will be the descent direction? I'm just talking about for this function also, what would be the descent direction? Descent direction where the dot product of this function with this gradient must be less than zero. Okay. For here, for this function also, we'll be having if this is the value, then perpendicular will come like this, and then you'll be having some. So you'll be having this yellow point as the descent direction for this gx. That will be the feasible direction also. So it's the descent for gx, but the feasible for this whole what you can say the for the whole whatever we are solving. Okay. So here you'll see that for the fx, for the function fx, for the gradient of fx star, you have got this all green point as the descent direction, and the descent direction for this g also you have got this yellow direction, that is the feasible also. So you'll be seeing that there are so many directions, those are descent also and the feasible also. So you can conclude that this x star was at least not the optimum solution for me. Okay, because I'm getting so many feasible direction, so many decent direction that was feasible also. So I can go and can find some other point also where the value will be lesser than whatever I have got till now. Sorry. So this is what we are talking about. So we have got. I'm really sorry. So this is a common point. This is a common point means these are the directions where the function's value was coming down, and also that was feasible. That was also satisfying the our constant also, our whatever the condition was given to solve that problem. So that was satisfying that also. So that's why this x star at least is not our optimum solution. Are you able to hear me right?
Yes, sir.
Okay. So yeah. So this was mostly discussed in the first lecture. So that's why this x star was at least not our optimum solution. Now we'll see what can we conclude between f, like the del of x, del of function and the del of constant. Okay, so we'll be coming up with some conclusion, some basic conclusion, where we'll be able to say directly. Okay, so from till now, is there any doubt in first lecture?
No, sir.
Okay, so we'll move to the second lecture. So I'll just go through the activity also. So if you're having any issue in any of the problem, you can ask. So the first one is feasible direction is the property of. So this is a basic like so generally the function like property of what? Can somebody say?
G of x.
Yeah, that's the property of constant equations. So that the direction can be a decent direction at a x star if the corresponding objective function value. What will happen if I'm able to find a decent direction in that direction? What will happen? So the function value will decrease, right?
Yes, it will decrease.
Which of the following condition is needed to satisfy to decide whether the point is indeed the optimum in case of constant time? Which of the following condition is needed to be satisfied to decide whether the point is
But both A
indeed
and B, huh?
Last option.
both A and B conditions are needed to be satisfied. So the vector D is a decent direction of the function if the dot product should be less than 0. So the second lecture will be just concluding some, will just come to some conclusion. Okay. So like for example, if the del of gx star and the del of fx star both are parallel to each other, if both are parallel to each other, then you can see that the all the gradient, all the descent direction are also feasible. So in the earlier condition, we were able to find some descent direction that was feasible, but now I'm able to get all the descent direction are feasible also. Okay, so this is the worst condition that I can expect, right? So like I'm able to get like n number of what you can say the all the descent are feasible also. So yeah, so here every descent direction is also feasible. So x star can't be optimum for this condition also. Now the third condition is I'm taking the both as anti-parallel. So del of x star and del of f x star and the del of gx star both are anti-parallel to each other, then what will happen? So this yellow part will become the descent direction for the function, and this green part will become the feasible direction, right? So now you can see that none of the point, like none of the descent direction is the feasible also, right?
Yes, sir.
So here we are not able to find any direction which are common to both. So this we are talking about the inequality, right? So here less than in the next lecture we'll be talking about the equality. What you can say, the equality where the constant will hold some equality. Okay, so here we'll see that. So what you are seeing, that this is simply the Lagrange. If somebody has read that Lagrange multiplier in the mathematics also, we generally solve most of the problem with the help of many of the problem with the help of Lagrange also. So here, so like that will help you to make some of the problem. Those are like pretty difficult. You'll be able to solve with the Lagrange multiplier in very like 2 to 3 lines. Okay. So here what happens? So both are like what? Both are anti-parallel. So we can get some constant lambda. So we are just multiplying that. So lambda fx star is equals to minus lambda. So you can take, like, you can exclude the zero, like minus also. For this example, we are taking lambda as a positive scalar. You can solve directly, like you can directly write this del of x star equals to lambda times del of g star also, where you will be taking lambda as negative scalar, right? Excuse me. Yeah. Okay. So this was our the third condition. Now we'll talk about the conditions where the constant will hold the equality. Okay. So whenever the constant will hold the equality, now we can talk about two conditions where, so here whenever we have del of fx star and del of gx star, if both are parallel also and both are anti-parallel also, then, like for example, this is not the condition. So okay, yeah. So I'll just talk about here for this function, like for example, gx star plus eta d. So with the help of Taylor, you can write this form. But what you need, you want this to be a zero, right? So like this is zero, then this should also be zero. So where are those conditions? So whenever these are like perpendicular to each other, so del of x g x star is perpendicular, like for this condition. But if del of fx star and del of gx star are at some angles, if both are at some angle, then you will find this condition, this feasible is also decent. My God. Yeah, so this direction you can say directly this is a decent also and feasible also. So what you need whenever these are both parallel or anti-parallel to each other, like here. So when del of fx star and del of gx star both are anti-parallel to each other, then you will find, so this is the line where both are perpendicular, where the del of gx star is zero, and that generally doesn't come under the descent direction. That's why you can take this direction. This direction can work. So, and here also, whenever the del of fx star and del of gx star are like parallel to each other also, so you'll find that for this direction where the perpendicular, like this direction, you are able to find a direction where the del of gx star, or the direction transpose of del of gx star is equals to zero. So you are able to get that, right? So if, so there is only two conditions. So if you are having the constant is having the inequality, then you will be able, in both the condition you can use the same formula, del of x star equals to lambda times g of x star. But one thing you need to remember, in the upper cases, whenever the constant are having the inequality, so in those cases the lambda will be positive scalar if you are taking minus. But if you are not taking the negative stuff, like the other conditions, where the equality holds, where the function, the constant was having some with some equals, like x square plus y square equals to 0, or x not 0 1, or something like that, where the equality will hold. In those conditions you can use the Lagrange multiplier as like del of fx star equals to lambda times del of gx star, where the lambda can be positive and negative also. So in the equality, the both the stuffs, both the delta product can be parallel and anti-parallel to each other, because we need del of g star equals to 0 in the equality constant. But in the other condition, in the above or the other condition where the inequality was holding, in those conditions we were not like we were the del of f x star and the del of g x star should be anti-parallel to each other. That's why we were using the lambda as positive scalar. If you are using the formula as del of x star equals to minus of lambda times del of g x star. Okay, so this is clear, right?
Between any point on this perpendicular line will be no, right? For every different point, there will be a different del of x star, and accordingly, there will be a the same line will not work for all x stars, right?
No, no. For every x star, the value. Really sorry. Yeah.
No.
So for every
You want to
x,
take a break, sir?
like I, I'll just take some water. Yeah. So for all the like values of x, the everything will become like everything will differ. This was your question, right? Or something else
No,
you're
no, I
asking?
got it. I got it. I got it. Because the direction of the gradient will change. So,
Yeah.
I,
At each
sir,
every month. Yeah.
I have just overall two questions.
Hmm.
The entire lectures. I'll say it now so that you can probably answer as you go along.
Huh.
One is, what happens if g of x is greater than 0 is the condition.
G of
X is greater than 0 or whatever, greater than some number.
okay.
If this is one. Second, all of this Lagrange multiplier, I know from a gradient descent point, we are looking for the minimum global minimum and local minimum. So uh, we are minimizing. But what happens if we are maximizing? It's the same thing.
It's the same thing whenever we are maximizing. What generally we do in the gradient descent also, what generally, like if we are minimizing something, so maximizing is what, like you can, if you have to maximize something, you can take minus and then minimize that function.
Correct.
So this is what generally we do in ML. Like whenever we need to solve some optimization problem, if we are having maximize, we generally take the inverse or minus term and then minimize that function. So maximize also you can do, but like minimization is like a pretty simple one to do.
Okay. And what happens when g of x is greater than 0 is given as the condition?
I think that should not make much impact, I guess, but I need to be clear about this. Like,
Okay.
like this
Okay.
is like some constant only, right?
It
There's
is a
some condition.
constant, but yeah, but let's say it's a some, let's say it's surface area related stuff. It can't be
Yeah. So
negative. It has to be.
yeah, like for example, x square plus minus one greater than equals to 0. So it will take a lot of values, right? Yeah. So in those conditions, the number of points will become like very large.
Okay.
Yeah. So if this is the condition, like for example, I'm taking a constant where the values will lie. This is our coordinate axis x and y, and the condition is like x square. This is the point will lie apart from this circle.
Sir,
So now you're having a large chunk of x values. But from those values, here only one condition should be satisfied. Like the point should lie after, like the point should lie apart from the circle. But the other condition is also there, right? So that the function should be minimum or maximum at that point. That is also the condition, right? So from these
Or
points,
or
we'll be
the,
get.
or the same thing can be applied. We can take the negative of gx and say it's less than 0.
Okay. Mm.
But gx is the limit function, Mr. Vasu.
Yeah, yeah. So that's why that we can't do. So see,
Okay.
like
I,
so
I don't know. I'm confused about it.
see. X like you have some condition, and the condition is like all the values of x and y should lie apart from this circle. But you need to solve this problem. With this some function is there, and you need to minimize that function or maximize whatever you want to do. But in maximization, like what happens, you'll be having like, okay, this is a minimization problem, minimization of x or y or something like that. So you have a large chunk of values, but if you have to minimize this function, you'll be getting like, if you have to minimize that function, you'll be getting a fixed point, right? You'll not get like, I don't think so. This will make any impact whether it's gx equals to less than equals to zero or gx equals to greater than equals to zero. This is not going to impact the function for sure
Sir,
because
but
yeah,
in case of g of x greater than equal to 0, the
yeah,
feasible direction will be the one in which g of x increase, right?
yeah.
So that's the change I think which we need to take into account here.
So if you are having gf, so you need to get that direction where the all the functions should hold these conditions, right? So okay, in that case, what will happen? Like here, you need some negative value so that the function's value should decrease.
So maybe
G of x should increase, right?
you can check later and get back to us on Discourse or something like that.
Okay, I'll look up on this. So yeah, so the till second, I think so. It's fine, right? So there's only the constant problem, and we have just started to solving the problem with the help of Lagrange multiplier. So there were two conditions only: whether the function is like holding some inequality or it's a equality stuff. So equality, you'll be using the lambda that can take negative and positive both, because the del of f and del of g star is like anti-parallel and can be parallel also. But in the inequality, it should be anti-parallel, so you'll be taking lambda as positive stuff. But in both the cases, you can take the function as this also, but this should you should be remembering, like if you are taking fx star in the inequality, when the inequality is holding, you can take this function also. But the problem is here, you should be remembering the lambda can be like lambda will be negative only. But if you are taking del of fx star equals to minus, like anti-parallel, you are doing the anti-parallel from starting, then this should be positive. Okay, so you can solve whatever you want to take, but the only thing is you should be able to remember that what you are taking from the starting, which stuff, which formula you are using from the start. Yeah, so the method of Lagrange is this one. So if you have to solve some problem, so if you have to solve this problem where you have been given the optimization problem as fx, you need to minimize, you need to get some x where the function is minimum. Okay, and you have to satisfy this condition also: gx equals to the constant function should hold this equality. Okay, so this is the, yeah, so here is the like one example where g x1 square plus x2 square was equals to 0. So this is the this is the condition that you need to satisfy, and this is the optimization problem that you need to solve. So this is the basic, like one example has been given how to solve this problem. You need to just take the gradient with respect to x and x1 and x2, and then you need to equate it. You'll be getting some lambda value, or so if you are getting some lambda value, with that lambda value you can get the value of x1 x2, okay, or xy, whatever you are writing. And if you are getting more than like one value, you need to check, and you need to check for the constant also, where the constant is satisfying or not. And then you need to check, and you need to find the value of a function. You need to put the value in the function to get the function's value, fx value, and whichever is the minimum will be the correct one if you're solving for the minimum. Okay, like here you have got like x1 as like two values. X1 is like root of 8 and minus of corresponding to the x1, you'll be getting x2 also. So now you have, so in the first case, yeah, he took lambda equals to -1, and then with the help of lambda equals to -1, he got some values x1, and then he got like x2, like, so these are the values. So he got four like paired of x1 and x2, and in all those four paired of x1 and x2, he would have checked the value of the function at those points, and whichever is the minimum value corresponding to that value, the x star would be the optimum solution for this problem.
May I
So
ask a question
yeah,
here?
yeah.
We have these two equations, right? F of x is equal to x square plus x1 square plus x2 square is equal to 1. That's a circle.
Yeah,
Sorry, g of x is, that's actually a circle.
it's a circle.
Yeah, and the one above f of x is it's quadratic equation, but what I want to ask is, what is the physical relevance when we are actually doing the gradients of two? We are only equating the slopes, isn't it? Delta f and delta g. If I take it as a 1D problem, not a 3D, sorry, 2D problem, not a 3D problem,
Hmm.
then I'm equating the gradients. What does this actually mean physically? Okay, the gradients means like there is a point on both these curves at which the gradients are equal. Is that what I'm actually trying to find out, or
It's
what is it
not
that's
like,
happening over
yeah.
there? Yeah, yeah.
So at some point,
Mhm.
the gradient is like we were talking, like the gradient should be anti-parallel to each other,
Correct,
like anti-parallel or parallel to each other. This is what we are
correct.
solving for. So we are just finding some point where
Mhm.
those points where so this is the one, and like the necessary condition
Mhm.
that if you are able to if you are finding for that optimum solution at that point,
Mhm.
both the gradient at that point for the constant and for the function should be parallel to each other. Okay.
Okay.
Okay, so this is what we are finding for. So if I'm able to get that solution, or that uh, corresponding to that anti-parallel or the parallel, that must be a multiple of some scalar, right?
Yeah, but it is not necessary that the gradients are going to be on the same line. That's what I want to actually. I mean to say the gradients could be parallel to each other
Each
for
other,
each of these curves.
yeah, parallel to each other, and anti-parallel also it can happen.
Yeah,
So
anti-parallel also, but they need not lie on the same point. Correct. That is my more important. I mean, that is what is
no, it should lie on the
bugging.
same point. So at the same point we are taking care, like we were discussing the last lecture. So if I'm able to find some, see, if I'm taking, like, for example, x equals to 3,
Hmm.
so you can't like say this x equals to 3 should hold gx also and fx also. So at that same point, the function should satisfy the conditions also, at the same point, that function should be minimum, right? This is what we are solving for. We are just solving to get one value where it should hold the condition also, and the function should also hold. Like we should be getting the minimum value at the same point, and that point should be holding the conditions also, right?
You're right, but what I'm trying to ask here is, yes, that is true, but e- without there is a possibility that these two curves need not intersect, isn't it? They don't need to intersect. When I'm looking only at the gradients and equating the gradients, they can be adjacent to each other, and I still can get a gradient, which I mean gradients which are parallel to these.
No, no. So if this is not intersecting, that means
Mhm.
what? It's if this is like, if this is not
There's no
intersecting,
optimal
then
position.
yeah, there should be not optimum position. That, because that is not satisfying about condition. That it should
Correct.
also hold the condition also, right? The constant it should hold. The constant, whatever we like, if I'm solving some problem, but
Hmm.
there are some conditions also. Like, okay, so if you are going here, you should be coming with me. So there is a condition. But if you are going alone, that's like it's improper, or what you can say, this is not the solution. So there is some conditions, like this should hold, like
Geom-
x and
geom-
y. Yeah,
Geometrically, it will belong to both the curves.
yeah,
Um, this is the point. Like if both, let's say take two concentric circles.
okay,
Let's take two concentric circles. X square plus y, x1 square plus x2 square is equal to 2, and x1 plus x1 square
Yeah.
plus x4 square is equal to 6. The
Okay.
gradient, if I actually one, let's say for just theoretical aspects, one is f of x, other is g of x.
Hmm.
So it's going to be 2x1 and 2x2 gradient for both of them. So if I say x1 is equal to x1 and x2 is equal to x2,
Okay. See,
then
if this is the constant equation, and you are
yeah,
saying that this is a gx, and the
yeah,
point should lie inside this, right?
yeah,
The point should lie. And what is the problem? Like, what is the effects for this? I need to get what, like some minimum value, or
yeah,
maximum. So if this point is not lying, or if you are not able to get some intersection,
right.
uh, so you are not able to, you're not solving this is not the optimal
Yes, I
solution for
cannot find
sure.
the optimal point.
Yeah, this is not the optimal point for sure. You're not able to find that.
There is no optimal point.
Yeah,
So
there should
that
be
will be the
some
natural.
yeah, there should be some, like the condition should satisfy for sure. That's why we are talking, like the first step should be, it should satisfy the condition that x star, when you are solving, when we, like somebody has told you like this x star is the solution, the
Mhm.
first thing that somebody should do is to see whether this is satisfying our the constant equation or not. If this is not satisfying, then for sure this is not the optimal solution.
Okay,
That's the guaranteed. Yeah.
okay, okay, got it.
Yeah.
Thank you. Sorry for the interruption.
Yeah.
Just wanted to be
No, no.
clear about the physical interpretation of these equations, mathematical forms.
Yeah, yeah, sure. No, it's like it's fine, totally fine. So yeah. Mhm. So with the help of Lagrange, we can solve like many of the problem, but not all problem can be solved with the help of Lagrange multiplier. Okay. So here, like we just briefly talked about the projected gradient descent. Okay. So here what happens? So in the gradient descent, we don't have any constant, like there is no condition. Whenever we are solving the gradient descent with the help of, whenever we are solving some optimization problem, and if there is no condition, then we can solve with the help of gradient descent. But if we have some condition that we are applying, or the constant that we are applying on the constant on the optimization problem, that the x and y should lie in this square or in this circle, then we are putting some condition on x and y. Okay, in those cases what will happen, we'll be using the projected gradient descent. This is almost same as the gradient descent only, but in this condition what happens, like for example, this is the point and this is the, what is the direction of the direction of the, what do you say, the f of, at the del of fx star. Okay, this is the direction. So what happens, generally we take the projection, and whenever we are taking, like this circle is the constant, or this circle is the condition on which the x and y or x can lie only. Okay, so what happens, we generally take the projection, and from that projection point we'll just find the shortest route to reach this, what do you can say, this circle or the red circle. So we are taking the projection on this constant, and from wherever we are like reaching after taking the projection, we'll just reach the nearest point that should touch this circle. Okay, or circle, or whatever the point this is, like this can be a square also. We are just projecting and we'll reach to the nearest point. Okay, and that point will be taking that as a value. Okay, so that's like in the gradient descent, what we are doing, we were not having any condition, so we can drop, like we can just solve with the help of gradient descent, because there is no issue of the constant, there was no condition, so x and y can take anything. But here we have some condition, because x and y can take some appropriate point. Okay, so if we are having some conditions, so what we'll be doing, we are just taking this pi, what you can say, the projection step we are taking, whatever we were doing the last term. So this is like not the, this is not like been talked in the great details, just a brief idea he has given. Uh, because he has to discuss regarding the convex function, convex sets or convex function, in whichever, like if you have convex function, then you'll be able to use this projected gradient descent easily or the Lagrange multiplier easily, you will be able to use. So mostly he has to discuss the convex function. So he just discussed a brief, gave the brief idea about the projected descent direction, projected gradient descent. So in this, what do you can say, the algorithm, we are using the same stuff with the gradient descent, but we are applying some function on this gradient descent. We are applying some sort of pi function, and that pi function, generally what pi function will do, the pi function will project the value on the plane of the constant, and then it will be searching for the nearest point from where he can reach, where it can reach the nearest, like the nearest constant point, and it will it will take that value itself. It's like here the formula is what, the minimum x minus y, this some y it has got, and this y should belongs to x sorry s. So I'm sorry for that, like I'm not able to speak properly, like yeah.
No, sir, not terribly sorry that we are making you do this.
Like I'm not like well for last, like from the
I
day
know,
I came to Delhi.
dengue.
Yeah, it's like the Delhi is not the place to live, like seriously. So like the projected descent, gradient descent is like it's a same as gradient descent, only we are applying some condition on the gradient descent whatever we were applying earlier. So in the earlier cases we are not having any constant, now we are having the constant, that's why we are applying some pi function or the projection step onto the gradient descent. So this is like, this has not been discussed much, so this is just a brief idea, so I guess this is fine till now, right?
Um,
Yeah.
Here also I have a question. When we are actually projecting onto the surface, okay, that part is clear, but why am I shooting out of the surface is what I was trying to understand.
But because we have some fixed constant, right?
Ah, okay, the
We
eta
are
you mean?
having some fixed value. Like for example, this is the circle. This is the fixed circle or fixed
Correct.
this point, right? But it can shoot out of that also, right? That's why the in the gradient descent, what was happening? If we are shooting out also, there's no problem because there was no such cases of where we were not able to satisfy that x to this condition where the x star should satisfy this gx star less than equals to 0. But here that should satisfy the whatever we are getting the x, that should satisfy this function also, right?
Uh, is it the eta that is making me shoot out of it, or
No, the step, yeah, eta you can, yeah, eta also, like eta is like a little bit of change in the value.
okay?
Yeah,
Because
it can like
xt will lie on the surface. Every time I do an increment to the next step, I am actually going out and then I'm projecting to come back in. Is that the way it is?
yeah,
Okay.
but this like it's like not, what you can say, talked in the any like brief, it's talked in a very brief here because we are not using here, it was just talked so that we can get the idea regarding the convex function and the convex state. That's
Hmm,
it.
hmm. Okay.
Yeah. uh, yeah. So from here it's like these are like some important aspect of the convexity and the convex function. Okay, convex function, concave function, quasi convex and quasi concave functions, so we'll be talking about those. So can somebody give me an idea about the convex set? What are the convex set or the convex what is the convex function, or what's the difference between convex or concave function?
Uh,
Yeah.
from what I understood, as long as the 2 points of within the function can be joined, it's okay. It's called a convex set. Otherwise, it isn't. So
Mm.
if I take a triangle and put a couple of points in there, They can be joined no matter what. But if I have a
Yeah.
amoeba kind of a shape, then it's not going to. But the concave part of it, I didn't really understand.
mm, So yeah. So if you have some straight line like A and B, okay. So all the point inside this, right? All the point. If you are able to join some straight line, so this is a A. So all the point inside this will come under this convex set. Okay, and you can write this as a some 1 minus lambda times A. So any point inside this straight line or the line segment plus lambda times B. So this is the some you can say the convex set. So and in the plot also, if you have some 2D plot, okay, if you have some 2D plot, and if you are able to what you can say the if you are able to get 2 point inside that plot, and if you are drawing a line segment, okay, and if all the point inside that line segment belongs to that set like S or whatever you are, right, like for example I'm just writing it like I'm plotting some plot, like this is a circle or this is the thing I'm plotting, okay, or this is the triangle. If I'm taking some 2 points inside this and I'm just plotting like any 2 point if you'll take in, so this is the straight line or maybe this is the straight line, or here also this is the point I can take, this is the point, this is the point. If I'm plotting this or I'm plotting this, so this is not the convex set because you are able to find something that is out of this set, right? Fine. And for this problem, if you are able to take some 2 point and like just drawing the line segment, and if all the point is lying inside that set, then you can say this is the convex set, okay. Otherwise, if you are able to find a single point also that generally lies out of that whatever the plot you have plotted, then it's not a convex set. That's the simple example, like the what do you say the definition of this. Whatever the plot it is, if you are able to take some 2 points inside that set, and if you are just drawing a line segment, and if for even for a 1 point, if this is lying outside the point, outside that set, then you can say this is not the convex set. So to have a convex set, whenever you are taking 2 point, it must all the point of that line segment must lie inside the what do you say the convex set whatever you have drawn. Okay, for this problem we are able to find some point that is lying outside our set, right? Okay, for example, I have this x1, x2 that is belongs to some convex set. So there's one question, I guess. So I guess where is that? Okay, so this problem, third one, x1 and x2 belongs to S. So S is simply, you can expect this is a convex set. No, this is not written here. Okay, so if x1 and x2 belongs to some set S, and x3 is what? X3 is like x1 0.5 of x1 times plus 0.5 of x2 times. That is also belongs to x. Then S is what? Can somebody tell me with the explanation? How come if this is a convex set, why and why it is not? If you're saying it's not the convex set.
This is a convex set because it's a midpoint.
Okay, but okay, so this can happen, right? This is x1, this is x2, but this can happen, right? This is the sorry, this is the line segment. Let's for example, this is a plot where it is going from here to here and then from here to here. So this is like, but x1, what do you say? The line is going from here to here and then from here to here. Okay.
But both of them belong to S. So S is a superset here, right?
So
See.
x1 and x2 necessarily have to be a straight line.
Okay, x1 and x2 belongs to, this is just written x1 and x2 belongs to some set S.
Yes.
Okay.
So
x3
x1
is a
x2
point.
yeah,
X3 is some point. Okay, so
x3
x3 is
is
like some point, and that x3 is here. X3 is this one, and this also belongs to x1 plus x2.
by 2.
This also belongs to S. So this belongs to S. This belongs to S. This belongs to S. Does
Yeah.
that mean then S is a subset? But this can happen, right? I can have some point where this is not the like this can be the function. This is the x1, but the midpoint is here. Let's for example, midpoint is here because midpoint is also coming under convex set. X1 plus x2 by 2. This is x3. But this is not the convex set, right?
Sir, but if we take different x1 and x3, then that midpoint may not lie on that set S.
Yeah,
What can you repeat?
yeah,
But
that's what he's saying. That this
essentially, this
entire
shape itself is not valid as a convex set, correct? S
that's
cannot
what he's
have the
saying.
shape. X1 and
This
x2
is
belong to
9.4.
S,
Yeah, so x1 and x2 is belonging to S here. X1 is here
but
and x2 is
S cannot have that shape because S is not a convex set on that count.
yeah.
Yes, S cannot be a convex set. That's what I was trying to say.
Sorry. If S is a convex set,
Yeah.
then S cannot have that shape.
Yeah, this is
Right.
what I'm talking. So
Agreed.
this is what I am also saying.
Hmm.
So this must not be a convex, right? Like this can be convex and can not be convex, right?
But what is
See,
the definition of S then? If S is, where should we actually, what should we assume? Is S a convex set or S is not a convex set? Because it depends on that now.
huh. So that's why that the question is like, see, if this is the plot, and if x1 is lying here, x2 is lying here, and x3 is lying here. X3 is what? X3 is x1 plus x2, right? So for this case, S is subconvex, right?
Yes.
But if I'm having plot like this,
Then the answer is dependent on S.
yeah, it depends on like how
No,
does the
they are asking, given this condition, what can you say about S? I ticked it as convex when I answered it, and the answer is correct.
Yeah.
oh
You are right.
The
You are right,
question
Mr.
is,
Vasu.
given this
Yeah.
condition, what can you say
Yeah.
about S?
Yeah.
But you're
but
right,
this
sir.
is not correct. This is not like the convex is not correct for sure here.
Yeah, probably. Now that you're saying it, it looks like
Yeah, this needs to be changed. Like this is not the convex. Like it's like it can be, but sometimes it won't be also, right? There is not given like x1 and x2 is a lying segment or something like that.
hmm.
So that's why it can be convex and can be non-convex also. So for this problem, like none of the this is correct. So I'll make sure this will be corrected. So there's an error here for sure.
And Mr. Vasu, you were having some question the other day also you were asking, right? About was it a 9.4 or
No, I think I don't call me Mr. Vasu first. Vasu is more than enough, Baba.
okay, Vasu.
The first one, the same
Okay.
9.4, but I got the clarification.
Yeah.
What
Okay.
was that? Can you share, please?
Yeah. I'll take. Okay. If
Go ahead,
somebody wants to say, yeah. So here what happens? X1, X2, X3 belongs to S. Okay. This is the convex set.
Mhm.
But the problem is the point x3 is equals to this one, and this is
Correct.
not written that x3 is lying under x1 and x2. So if this is the condition, like x1 and x2 is like x1 and x2, and if x3 is lying inside x1 and x2, x3 is lying like this, then lambda will lie from 0 to 1. But it's not given here ki x3 is lying inside this line segment. X3 can be anywhere. Like this is the plot of a convex set. X1 is here, x2 is here, right? And x3 can be some other places also, right? So lambda can vary any, like if this is the condition, if it's written x3 is lying on that line segment, okay, joining x1 and x2, then lambda will belong from 0 to 1. But if it's not lying, then lambda can take any values, right?
But how can it actually move away from that? Okay, just maybe if we go back to the question once, please.
Yeah.
Okay. It is not mentioned as to
Yeah,
lambda.
lambda
But
can take any.
no, it's a linear function, right? You take any combination, any lambda, it will be either within x1 or x2, or it will be outside of x1 or
X1
x2,
and X2.
right?
Yeah,
But
it
it will
can.
be on that straight line.
Yeah, it will be under a straight line. That's for sure. Okay, that's fine. But it can go apart from that. Like it can go here also, right? So the lambda, like for example, if you are taking lambda as 5,
Okay.
if
Yeah.
you are taking x3 equals to 5x1 plus for some minus
It can be
4x2,
minus 4x2. Yeah.
right? So it will go somewhere else, right? Like for example,
No, but x3 also belongs to S, right?
yeah, it belongs to S. That is fine.
Acha,
So this,
but it can be anywhere on that line. Correct, correct,
yeah,
correct, correct. Correct. So it could
yeah,
belong. Yeah. It need not be only 0 to 1. Correct.
yeah, it can take any value.
Yeah.
Is this clear?
Yeah.
Sir,
Yeah.
sir, could you go to the previous question, like which we were discussing?
This one.
Yeah. So
Yeah.
I think here for all x1, x2 belongs to x, x3 equal to x1 plus x2 by 2. If that is the condition, I think this would be a convex set S. So there should be for all x1, x2.
Yeah. If this is for all, then you can say,
So yes. So this is wrong basically, no?
yeah, this is wrong. That's why I told this none of this will happen here. Like it
No.
can be or it can be.
Right. Thank you, sir.
Okay. So the convex. Okay. So I guess the only thing to check the convex set is the line segment. If you are able to draw the two, if you are able to take some 2 points, 2 point laker, and if you are able to just join the line segment and the line segment, each and every point of the line segment is lying inside the set, then it must be a convex set. And if you are able to get even a 1 point that is outside the set, then it's not a convex set for sure. And the most important thing is in mathematics, how generally we check the convexity. That like when I used to study, like at that time, convex function I used to read like convex function and concave function. So here the d2, whenever you will do the difference, double differentiation of this function, so this should be greater than 0. Okay, like for example, x square. So this will go like this. Okay, if you are able to the dx square like d2x d2y by dx square is positive, then it must be a convex function. And if the d2f d2y upon dx square is negative, then it's a concave function. This is the most important aspect that I used to check for the convex function and the concave function. Okay. There are also other aspects. Also, there are so many properties of the concave and convex that I'll tell you. But
So
yeah,
if
so
minus x square, if it is taken, it will be less than 0. That will be a concave function then.
minus x square. Yeah.
Yes. So it's like this. If it's like a cup, right? Then it's
Hmm.
convex. If it is the opposite, then it is concave.
Yeah. For this example, you can say. So normally, and there are some other function also, the quasi-convex, quasi-concave that generally
Yeah.
we
It's
read.
like in optics, there's a concave lens, convex lens, right? Exactly like that.
Uh, yeah, but I don't know exactly it will be
No,
like
no, it
that
does
or
this. It does the same function. It converges all the sun rays at one point because it's a convex lens.
okay,
It
which one
diverges.
converges? Yeah, convex lens generally converges our point to a one.
Correct,
Like it's a
correct,
converging convex lens is a converging and the generally we use for the myopia, I guess, right?
correct, correct. No, not just myopia. Everywhere, if you want to bring it to, if you want to focus a laser at some point, then you use a
Uh-huh.
convex lens.
In a rear glass also generally use, I guess. Yeah. Uh-huh. Not the no convex, not lens. Generally use the convex mirror to the rear glass.
Correct. That's
But the shape, I don't know how generally we used to write the convex in that. We studied in class 12th or 11th.
okay, sir. It's the same principle. I mean, broadly, I remember it like that.
Hmm. And there are some properties also, like for example, yeah.
One point here. if we say minus x square, it is a maximizing function. If it is
Correct.
x square, it is a minimizing function.
Right.
So
Right. So
when
which
we
is why
say
minus x square, it will be like a reverse cup, and you'll
correct
have only a maxima. You will not have a minima.
minima,
This will be like this x square minus x square,
okay,
and
that's the
x
reason why
square
we
will.
call it concave. Okay, fine. Okay.
The
See,
from whatever I know, all loss functions are written are reconstructed to take a convex form, because then it's easier to find the global minima.
Yeah.
because we can use all the algorithm also.
Okay.
See, mainly, see, what is this then? This, can somebody tell me this type of function?
It's a
Exponential. Logarithm.
log,
No.
no,
Logarithm is like
Ex-
this.
sorry, this is a
exponential.
ex, no,
This is
No,
it's not
exponential.
exponential.
so. This
It's
function
not.
I told you. If you do the double
Reverse
differentiation,
exponential.
you'll get negative. So this is a convex type concave function. If you are going like this, if you are increasing, but if you are going like this, this is a concave function.
Yeah.
So the
If you
best way to
complete it,
check
you
is
get a
to,
reverse.
yeah. So the best way to check is the double differentiation of this function, and you'll get some negative value. There are some basic properties also that I can remember, I guess. If you are having concave function, so concave plus concave, all this will be concave function, and convex plus convex will also be convex function, and concave minus convex will be concave, and convex minus concave will be so the whatever the first term will come will be the final result. So concave plus concave is concave, convex plus convex is convex, concave minus convex is concave, and convex minus concave is what I told in the first term. Convex minus concave is convex. And if you are having like f of g function, so there are like lots that we can read about the convex, but yeah, so not concave. Here we just have to read about the convex function. Okay. So yeah, so we were discussing about the sets of the function, the convex set, and we already have discussed regarding this. So if you are able to plot that, then it's fine. Like here also we have some example. Just the basic. If you'll just now you can just go through the uh, slide ones or the lecture ones. He has taught like very like nicely. And some properties that you can write out, the intersection of two convex set is the convex set. And this is written here. The property is like the if S1 is a convex set and S2 is a convex set, the intersection of both will be a convex set. There are also some properties been discussed here.
So can we move to convex functions, and then the last part, which is the global minima, local minima? So these are,
Okay.
if nobody has any problem.
So yeah, so I'll just move there. So convex set was just like this. Like if you're able to just get an idea about the line segment, and if you have some, so only the only thing to know about the convex set is the line segment. If you're able to understand them, that it's like fine, and you'll be able to solve any problem. Convex function, like there are like three ways to determine. One is like if you're able to double differentiate that, and if the value is coming to be positive, then it's a convex function. The other is like epigraph. Epigraph, if you're able to plot the epigraph of any plot, and that epigraph is a convex set, then it's a convex function. Like for example, epigraph is what, like for this plot. So this is the epigraph function, like x, z, and where the z is greater than the function's value. Like this is a plot. What is the maximum function value at some point, like x1? This is the function value, right? Like for example, this is a plot I have. So this is a plot that I have. So for some point x1, this is the fx1. So greater than fx1. So this is the value at x2. So this is the function fx2 greater than fx2. So all those points greater than this. And if this plot is a convex set, this you can say this is a convex set because you can take two line, any two line if you are taking any two line, you are able to see that all the points will lie under this set one. You can take any point, this two line or this two line even, all the points will lie inside this. So this is a convex set, right? If this is a convex set, this is a convex function also. So this plot is a convex function. Okay. So what you need to check, you need to plot the EP graph of any plot has been given. And if that EP graph is a convex set, then this is a convex function. Okay. So all the point inside the EP graph is a convex set, then it's a convex function also. So this is the one way to check. The other way I already told you to double differentiate that and check whether this is a negative and positive. That's the other way to check. And the third one, I guess there are some other things also has been discussed. And this is also the other aspect that you can check. How can you check that? If you are able to take like x1 here and x2 here, and if you are able to calculate the function's value at x3, and that x3 is what, lambda x1 plus 1 minus lambda of x2, and if this function, if the function value is less than lambda of fx1 plus lambda 1 minus lambda for all the values, then this is also a convex function. But this is pretty difficult to do that. But this is just for the sake of like it's a definition. He has also discussed about this also. This also you can discuss, like this is some with the help of the plot, like for example this is x and y he took. Okay, fx function of y is greater than equals to fx plus y minus x ka transpose. This is what, this is generally the y minus x ka difference. So this is the y minus x ka difference, and this is the del. This he took just the tan theta here. From here the tan theta he has calculated, and then he has written like this. This also you can just, if you'll just skimble the pane and you'll write, you'll get this definition also. And the last definition is the same. If you are able to, yeah, this is also, if f is a convex, then if and only if h is a if h is a positive semi-definite or the positive definite matrix, if you are having, then this is a convex function itself. So this is the Hessian matrix. The Hessian matrix, everybody knows how to calculate that, right?
Yes, sir.
Yes, sir.
So if you have been given some function, you can just calculate the Hessian matrix, and if that matrix is a positive semi-definite or the positive definite, then you can directly say this is a convex function that we have been given. So the first step is to calculate the Hessian matrix, then check whether this is a positive semi-definite or the positive definite, and if this is a like positive semi-definite or definite, then you can say this is a convex function. How to check the convex? How to check the positive definite, whether this matrix is a positive definite or not? You can just calculate the eigenvalues. If this is greater than equals to 0, then it's a positive semi-definite. If you are getting any eigenvalues as 0, and if all the eigenvalues are positive, then you can directly say it's a positive definite, and this is a convex function also. Okay, so now we'll move to the next part. So yeah, so here for any convex set, so the local minima will be the global minima. This is what I was like you were asking, right?
So see, sir, that's what I'm very confused about. The theorem is fine, but see, I have three local minima, right? There is x1,
Okay.
x star. Visually they are different. How can they be all global minima? Because the theorem says that if it's a local minima, then it's also global minima.
But this is then this not, it must not be a convex function, because this is not a convex function, right?
Acha, if f is a convex function, okay.
If f is a convex function, then only it will happen, because this is not a convex function, because you can see that you can take some point, and if you draw the straight line, you'll not be. So this is not a convex function. That's why. Yeah. So this will be applicable
But then a convex function, all local. But can it have multiple local minima, convex function?
I don't think so, because if the moment is
because that's then the words are see, that's what then all local minimum, then there shouldn't be a word minima, right? Minima. See, and in the question also there is a graded, there's a AQ. I'll just go to the AQ. I don't know which one that is.
Hello.
Yeah.
I
Yeah.
think it's possible to have multiple local minima. So if we consider a function which has a flat base, so for that function, all the points on those base are local minima.
And those are global also.
Yes, local and global both.
Correct,
So
like
yeah,
triangle.
Like a box, an
like a
open box,
ball also, even a ball with.
open box. So open box has a flat base, na? So all those points on those base are local minima, and also they are global minima.
Hmm.
See, okay. So can you tell me what about the sin x?
No, that's not a convex function, na?
This is not a convex function, yeah.
No. So if we draw a function like an open box, for
But
example,
if I'm talking just about from here to here, then you can get one local minima also, and that is the global minima also, and that is the convex set or convex
yes,
function also, right?
yes. If we restrict in this domain, then yes.
Yeah,
Yeah.
but so if you see this question, that AQ 9.65, AQ 9.56,
9.6.
question 5. Which of the following is true about a convex function? Uh, there may be multiple local minima, and local minima is also global minima. Right? The local minima is global minima is clear, but I wasn't clear that they can have multiple local minima.
So see, so what they have given there. See so this is what he was talking about.
Yeah, now I got it. Now after he explained, I got it.
Yeah, there can be some state point where the local minima can have, but it must be a global minima also. But there can be multiple also, right? Multiple means not at the different point, at the same point also it can happen.
How, sir? Geometrically, I'm not able to visualize.
Okay, you can valley you can imagine valley.
Yes.
A valley have a large number of point where the what you can okay I'll just you can non-positive indefinite function. Okay, I'll be having some image also. I have that or not. Okay, I don't have that. Okay, I'll just search it on the Google. Okay, so you can expect this type of function. See, so this type of function. So where one of the plane will be having the minimum value, or you can say this box, this type of box where
Yes,
the all the points are having some minima value. This is the minima, right? And this is a global minima also.
Yeah, this is the only possible way. There has to be multiple, like the base has to be flat in some way.
Half like in the valley also you have some flat like all the if
Yeah, yeah,
you calculate the slope all the point the all the for all this plane itself the value will be minima, right?
correct, correct.
And this is a convex function also, so you can say this can have more than one minima, local minima. So in the this week it was like mostly the convex set, convex function, and how generally you solve the constant optimization with the help of Lagrange multiplier. So I guess this is clear. If somebody has not seen the lecture, you can just go and can see the lecture with like some increased speed, and I don't think so there will be any issue in that. So when is the deadline? 9th, right?
Yeah,
So 9th, so maybe we'll be having that session, one session that is the maybe the doubt clearing session and the solve with us. Till that time,
one of them should be enough, sir, not more. One should be enough.
yeah, one session only that solve with us uh, on the Tuesday, like day before the deadline will be there. So if you have attempted the graded till that time, you can just ask regarding the graded problem, we can just give you a brief idea about that, and then the solve with us will just solve some problem. And the quiz 2 paper has already been sent out. Uh, that is from like week 5 to 8, and the problem can be some problem can be a bit difficult than the last quiz. But yeah, we'll discuss regarding that in the revision session that will happen maybe next week.
Will there be a revision session for SVD and
So okay, yeah, there will be the revision session for the SPD and positive definiteness. This is what you are asking, right?
yeah.
Yeah, so there will be the and but if you want to have a Gmeet session where like some people will be there that will not be going to the YouTube like streaming and all, that also we can arrange.
Sure.
But
Sure,
I just
definitely.
asked on the Discord, nobody has replied. Like I was like,
Oh, sorry, I'm not following
No,
this.
you just asked yesterday, sir. So we'll reply.
okay,
So, sir, for functions like if you go to the practice assignment for questions
okay,
like let's say anyone actually you can take like for example point on like 13,
yeah,
right? So y square is equal to 1 plus xz, that is some kind of surface closest to the origin, right? So which find the points on the surface which is closest to the origin. One is take each one of them and check the distance and answer. Uh, the other way, I did it using coordinate geometry. I didn't know how to use, any of these. It has something to do with, like, I'm guessing minimization. Uh, but I don't know how to approach these kind of problems. The tutorials also didn't have it. Like, there was a graded assignment question. I won't give the answer, but they said, what is the closest point to the plane from the origin? I just used coordinate geometry.
so yeah, with the help of coordinate also you can solve. What
Yeah,
was the
but here
problem? The practice assignment, right?
yeah. I mean, there is a similar problem in graded assignment, but even here, I used coordinate geometry. I didn't use any of these techniques, is what I'm saying. Like, I didn't know how to approach this.
Okay, okay, well, let me open that. So they have not uploaded anything, solution and all.
Week 9, not yet. Practice essay. I think till week 8 they have uploaded. Week 9 is not yet uploaded.
Yeah, week 9 is, I already sent them. Okay, I'll just open that. I'll just upload that.
Week 9 only after submission you would be actually uploading, right? Or before?
Practice we can upload.
Practice.
We
Okay.
can.
Yeah. That's not a bad idea.
This is this thing is because the pollution situation in Delhi, or you have dengue also? Because I remember somewhere you wrote you're recovering from dengue.
Yeah,
Okay.
yeah, the policy, I am not going out.
Yeah, but it's still four. Yesterday or day before it was
It was
491
like
AQI.
500. Yeah, it was around 500. Like I just saw on my phone it was coming. And I was like, what the hell is this? Every time it happens in like November or December.
Yeah,
Like
there's
every
Punjab problem. But now Kejriwal has said he will sort it out.
Kejriwal is almost same. All the politicians are same. I don't know. This is the week No, this is the 10th week, I guess. This is 7th week. Where is 9th week? Yeah, is this the one?
Yeah.
So the first statement, if given this fx1 x belongs to S, then this also belongs to S. This is a true statement. Has somebody solved this first problem? This, yeah, this is fine. Did somebody solve this one, first one?
No, not yet.
Okay, practice assignment you have not solved. Okay, so which problem you were asking? Ninth one, right?
Yes, similar problems. Like if you take like 13, problem 13, uh,
Yeah, so the 13 one is this one. Find the point on the surface
13,
of y
yeah,
square.
13, 14, 15, they're all similar. I
Okay.
just wanted an approach. Like I'm not
Okay.
looking for an answer, but I used coordinate geometry, but how do we approach it from a minimization
So
point
the
of view?
optimization problem, right? So this is the optimization the problem that you need to solve. Y square equals to 1 plus xz. What is the constant? The constant is not. Sorry, this is not the con. This is the constant, right? This is the condition. Find the points on the surface. So the point should lie on this surface. This is the condition, right?
Correct.
Okay. What is the optimization problem? So the problem is what? Find the points on the surface that are closest to the origin. Okay. So that the point should lie on here, but that should be closest to that point. So the distance you can calculate from any point. So the distance would be what? From the origin, x minus 0 ka whole square plus y minus 0 ka whole square plus z minus 0 ka whole square, right? So this is the optimization problem that you need to solve. So you have two
Basically,
equations now.
basically you have to create a distance equation and then solve for that.
Yeah, so this is the problem that you have. So now you can start
Sir,
see
we
this.
could also minimize distance square, right?
We can minimize distance
Yeah,
square.
yeah, yeah. Distance is square also you can whatever you want
Yeah.
to whether you
The
are
square
minimizing.
root is there, na? So that would like complicate things more. That's why.
Yeah. So then it will become a bit complex. Yeah, correct. So yeah, and this type of problem you can expect in the exam also. Like in the quiz too also, not you'll be using the what do you can say? You have to go with the basic approach, but yeah, even if you are good with the this optimal like Lagrange multiply, if you but the problem is in those problems there won't be any constant. Yeah, so you need to go with the basic approach that you have been discussing in the YouTube. So just now I remember there was some problem that was like this. That's why I told you now.
What do you mean by basic approach, sir? I didn't get that.
Basic approach means like for example you have some point, right? So so you have mm, this is the coordinate the x and y. So you have some like for example there is a point. A is here 3 comma 1. Okay. B is here some 4 comma 3. So the constant that has been given here is like the point should lie in this one. Like here it is 1 point V. So you need to minimize this VA plus VB you need to minimize. Okay. And the point should lie on the x-axis only. So how will you do that? You can just take x comma 0. The
Correct. You
distance you
can,
can
yeah,
calculate.
you create, correct.
Yeah, and then you can need to solve. So this type of problem you can expect in the exam. Okay. Almost I just told the almost not the same, but this type of problem you'll be getting in some like in the quiz also.
Got it.
Yeah. So we'll discuss this type of problem in the mock. I'll be giving you and the revision session also.
So
Yeah.
we'll be calculating the distance using x comma 0 as one of the points, 3 comma 1 and 4 comma 3,
Huh.
and we minimize for x. Okay.
Yeah, you need to minimize. You can calculate the double differentiation first. You need to equate it to
Yeah.
0, get the value of x, and then check whether it's a minimum or maximum.
Okay,
Yeah.
that's what you meant by the basic approach. Got it.
Huh.
Okay.
Sir, the code for quiz 2 is from which 4 to 8?
What point?
Code for quiz 2? What's the code for quiz 2?
It's 1 to 8, but focus will be on 5 to 8.
Acha, syllabus. Syllabus will be from
Yeah,
5 to 8.
syllabus, yeah.
Okay. Yeah, syllabus will be. I was not able to hear. Yeah. 5 to 8. All the problem will be from 5 to 8. But you already know that third, fourth week also consists of eigenvalues. So if you are getting some
Yeah.
problem on the eigenvalues, eigenvector, nobody should say like it's from 3 to. So yeah, mostly from 5 to, like mostly what? All the problems are from 5 to 8 only. But yeah, eigenvalues, eigenvectors concepts is also there. So yeah, this I'll upload. This will help you, I guess, in the graded solving the graded assignment. Okay, I'll upload this one. Anything else from this week, 9th week? Maybe you can just, if you have not seen the lecture, please go and watch. This professor is really awesome. I can tell you. I've done some courses in IIT Madras under him. He was like awesome. He has done his, I guess, PhD from ISC Bangalore, I guess.
No, he's very, very good. All three actually are good. He's also very good. Surprisingly, all three lecturers are from ISC Bangalore.
Yeah. All three, or I guess Harish sir is from
I think
IIT Madras.
all three are from one second. I remember I saw that and I was quite surprised.
Yeah. He is also from IIT Bangalore. Yeah, correct. And then he did this. Yeah. He's from IIT Bangalore only. Yeah, but Prashant sir has done his BTech and MTech from IIT Madras. That I can remember. Yeah. So from this week, anything else is there? You can ask.
Can I ask
Yeah.
something about the question on graded assignment?
Yeah.
Can you bring up the graded assignment, please? The last
I'll just
questions.
Graded assignment, right?
Yeah.
This is what I was asking. The same thing.
Not the solution. Yeah.
Yeah, not the solution. I'm saying it's the same thing. Like, you have to create the distance equation and minimize.
No.
Yeah, you need to create the distance.
Here, it's easier to solve. I mean, like not easier, as Vasu was also mentioning a little earlier. With coordinate geometry in the head, it automatically comes faster. So how to
you
think
can
like
solve with the help of coordinate geometry also. Like if you are able to solve the first one, second one will get solved itself. You
correct?
just have to add the r, like
Exactly.
the radius.
Exactly.
That, yeah.
Exactly. So
No,
here,
actually, sphere and point is difficult. But if you take this one, for example, if you take question 9, this is easy to solve.
Yeah, this you can
Very,
solve with the coordinate also.
very easy to solve. Just one formula.
Yeah.
Which one? 11th. Which one?
9th is what he was mentioning.
Yeah, 9th is straightforward formula.
This is the straightforward formula. The point
Shall it say
and
something even easier, Vasu?
there could
Of
be
the 5, 4 of them don't lie on the line.
Yeah, that see that all that also you can also do.
Yeah, I'm like, why is this even being asked? If, oh, I left it at that.
Oh, I don't know who said this question. This was prepared, I guess.
Of the five, four of them are not even on the line. So there's only one answer possible there.
Then you find out the distance anyway.
Yeah.
Even there
You
is
don't
a
need to go. It's
formula
done
also, yeah.
already.
Yeah, even there is a formula direct, like yeah, here like the points has been given so badly that like you can find it without even the formula. But then it like you can just drop the perpendicular from that origin and then you'll get.
Yeah. So the last two problems, uh, there we are trying to maximize and minimize the distances. Is that the way it is with the coverings with the defined
Yeah,
spheres? Okay.
yeah, yeah.
I will
But you
try
just have
that.
to solve. Yeah, you can just solve for the minimum and then add it
Yeah.
the radius you can add. Yeah.
Yeah. Yeah. Okay.
Mm.
That's all,
Anything
sir.
else?
We'll leave you to go and take some rest.
Yeah. Thank you.
Yeah.
Thank you
Okay.
very
Yeah.
much.
Yeah. Thank you. Thanks a lot.
Thanks everyone for joining.
Thank you.
Bye. Bye.
Have a nice day. Bye.
Thanks, sir. Get well soon.
Bye. Bye, everyone.